start that wasn't started. Um, in terms of a larger scale collaboration with all remote teams doing other things as we do this here, because information is the bigger part of the process. I mean, once you do one build, right, and then say you record the kernel of information behind it. If that build and development leading to that point has been considerable, then think about, multiply that. Someone replicates that. 100 people replicate, 1,000, a million. I mean, that's the kind of goals we have, and therefore you can see how important the documentation is. Getting many people involved for the reason in collaboration, there has to be a deep purpose to something, and if that mission is good, like, oh, we're going to solve housing, okay, that's a big, hairy, audacious goal. Then you can actually get all the people on board to make that whole process happen, and that's why I'm pushing that. It's like, we're not seeing that yet. I mean, working hard to it. That's my mission to deliver an ability for humans to collaborate on scales unseen before. I mean, that's the basic goal. And here, that's a prelude to. Would you guys like to actually take out a computer and take notes while we're doing this in the same document that I'm on, or forget it because we're too stressed for time and things? Okay, but that's definitely what we'll be doing in the future. Maybe like in the future builder crash courses, just formalize that. I mean, for example, a thing like, oh, we have a class, actually set up a classroom space where actually there are desktops and it's already booted up to that page. It'll be super easy for you to edit. It's like having an app in front of you. So we can make all of this much easier. Right now, it takes too much know-how. I mean, too much for now. Okay, so let's boot up the same review what we've done yesterday. So basically the numbered regrouped version of the latest one that we have in FreeCAD, just to see what we've gone through. The major thing that we discovered yesterday, okay, so there was some of that bowing of the foundation, and it's true. I mean, that's actually, when in retrospect, it's like, duh. It's one of those, don't be stupid 101 things. I mean, the 2x8s that we're using, we had the posts on every 10 feet, 12 feet between the sections. The span of a 2x8 is about 10 feet, so it's gonna sag on you definitely. So right now what I did was, I'll show you actually a picture of what happened, what we did, and what the result was. So in the photos, look at this thing here. So hey, the photos didn't update. Let me see if they can come up there in real time. Sometimes the Google Photos typically update readily, but right now they haven't updated. As we speak, they should get updated. What we did here is every 10 feet we supported it. That's cool, all right, because the span in the joist direction, you've got 10-foot span. It's actually 10 foot 6 inches. Well, for the 20 feet, that's actually just right. So that wall came out good, but we noticed major upheaval when we got to the second wall with the sag. And in this wall here, as you see the detail right there, we actually already have that. So that's why these walls worked, and nobody picked it up. I did not pick that up. So these walls were relatively benign to do. But then what happened, so let's refresh here. Then, look at this. Man. So this is actually after correction. And what's happening? This thing is in midair. What happened? We already attached it to the next one, and was attached on a foundation that was sagging. So it's crazy how it worked out. So let's actually describe that process. So right here, okay, we're going at it. No support in this 12-foot section. You have to put a support in the middle. So when we're doing this, things started to go awry. And Suzanne noticed that when she measured with a long level. This is pretty much after correction. That's not really a space. That's like a pretty tight, good gap. But before that, that's after the correction. I don't have a picture before the correction. But what happened? So we do this. So this is how that was the solution. Cut yourself tapers, like out of lengthwise, grain-wise, not across the grain, but grain-wise. Cut yourself some slivers. Those are tapers that were like more like 2 or 3 inches on one side and tapering down to 1 or so inches less on the other, and whack them in with a hammer, and that's called a lever. That's leverage. You're creating motion. You're sticking it in like over a 12 inches to raise it 1 inch. So it's a 12-to-1 advantage with a heavy hammer. That actually is enough to lift it up. So it did lift it up, and after that was before some of the before shots, and then afterwards that's after it got lifted. It turned out we actually screwed those in when the thing was in midair, when the thing was not altogether. But after fixing that, before and after. So bam. So I mean that's important. We gotta make sure we support them in the middle, and we have to do that for the next section as well. So make sure before we start that we straighten this out. Back to the CAD. Hide the veranda. So this is once again you go and we're using all the tools that we can. Yes, there is that. I mean, this is what we have when we build this thing. Yeah, I mean this is pretty much an individual unit. The thing that actually puts it together. So if you look on the other side, because that's a complete break in a house. You gotta make sure you button up the top. So what are you doing? Into the top plate. So this is what we're going to get on as soon as the second top plate is on, we're going to start doing the trusses. So maybe orthographic view. So orthographic is easier to handle. So what we'll do is make sure we get solid nails into this 2x4 here, into the top. And then actually all the tops of the trusses are fixed, bonded together with the OSB on top, so that if you screw in, so the edge joists, these ones, they have two 2x4s reinforced, so you're screwing in through two 2x4s to each other over a structure that's pulling as one. So you've got that force of 1.5 inches of wood plus the OSB and then another, so you got 4 inches. You're making a connection to that to bond the top together, so you close up any of the gaps, like that gap here. Once we do the two trusses together, if there's any gap, we should close it up, because the wood is still flexible. Now those modules on top, there is a little bit of gap in there. If you look in there, taking some pictures. Let's see. Well, right between, this was actually interesting here, because at the very, very top you've got this big header. You're connecting it against that. There's like nothing to screw into there, because this one had a double, so it was kind of hard to bond it together. Let's see, do we have any pictures from the other side?
I guess that's a good example where that top plate comes in on helping join those together then, no? Because we can only get, so many in there, huh?
Yeah, the top plate would be useful, but now we're going to kind of rely more on the trusses now. There's also more layers that bond it together, and the steel, which is, it's very thin steel. It's called like, what is it, like 20 gauge or something. But steel over a whole length that's still like bonds it together so it can't slide apart. And it's a little more reinforced.
Where's the steel at?
So the outside cladding of the entire house is barn metal.
Oh, okay.
And we also use that for the front of the veranda. There was the soft membrane on the top of the roof for the main part, but everywhere around we've got, structure is white with some corner trims around that. Okay, so that's what we experienced in practice. So now, as we go forward, just to review, just go through the procedure again to, let's get this, and also like for the rain purposes, we got rained on. For rain purposes, let's get the first roof, the truss is on, so that starts with, you got the top plate like this, so let's get the double layer on. Once again, what's that? How about one? Trusses, they all come up on, and how do we do them? We probably bring them in, set up two teams on scaffolding, so one scaffolding and other scaffolding on each side, just bring them up, put them in place. And where do we line that one? Just flat against the top plate.
Okay.
Is it?
Flat against the outside, the exterior.
Yep.
Okay.
It's exactly even with the top plate
Yeah.
because this, yeah, remember we still have OSB that's going to bond this to the bottom of the house. Remember the top sheathing, remember that? We still have that. We still have another layer of sheathing that connects the very tops. So as you
Okay.
see that, it's right against the final trusses, but in the front we have the box. So if we go further to OSB rim, there's that. 3 is 2x4 rim. Those are 2x6s actually, remember that one. 2x6s for a solid connection to the front. So after the trusses, you got the sheathing on it and the 2x6s across the whole front and back. The side doesn't because we've got the surface of the truss to work with, and that truss is already reinforced with 2x4s, so we can screw into that solidly. OSB rim, 2x4 rim. Okay, let's do that again. So let's hide the sheathing. Trusses. Now let's get that in there. Right. Trusses. OSB rim, front and back. You got to bond them together, otherwise they could just fall on you when you're walking up on them. So that's 1 and 3 2x6 rim, and here I can rename that 2x6 rim. Okay, 2x6 rim. Tapered box, so that's what you guys have been working on inside. Okay. Now, how do you put them together? How do you attach that? Toenail. I mean, that's pretty much that's what we got. You can use long screws, but we don't have so many long. I mean, just toenail it. From the front, you got to toenail it into the 2x4 right below it. Toenail everywhere, because you got meat. You got 2x4s underneath it, so you got plenty of space because it's in the middle of those trusses, so you can get a nail in there readily.
How do we get the box up there?
We can start it we can go from the side and get it with the tractor. We can get the rim over it, and then we have to pull it up there. That would be the process. The tractor can get us quite a bit. I can, with the forks, I mean, the top of the bucket is like 10 feet. Right now we're at about 10 feet, so you're marginally making it, and then I won't be able to like deposit on top. It kind of have to bend over, and you can just, an operation there. We should get out 4 sets of scaffolding so that 4 people are at height. So on that small platform, the 12x20 we've got, that's decked with more scaffolding. So four teams, like 2, or 1 person, whatever, however many people we have. Now, roof box ledge. This is the thing that's important for the purposes of water between sections. We discussed that, how we're going to drape a cover over the top. Now, okay, that's a cool question. How do you join these two together? I want to fix those. View. Workbench. Let's go into part design. I'm trying to do the appearance, hide the transparency. Okay, we've got the box. How do we want to put those together? I was thinking staples. Staple them together. Each staple has a 25-foot force holding on each leg. Staples are 1 inch wide, right? Why not? Why don't we do that up there? Because so we're putting in the first members. We can't put this in as one piece. We put that all in separate pieces. How do you attach it to here? To what's below it? Well, you clearly have surfaces against which to attach. That's not an issue.
So it's pancake from the outside.
So we're at the roof box. the top ones, you take it up there, take the longest 2x that you've got, then take the next one, grab a saw, just cut it off in place if you can. I wouldn't measure it and then go on. Measure it, go down, mark, cut, bring it up. I would go put in a longer piece in, cut it in place. You got a measure mark already, if you can do that. That would save you time. Yeah, staples. Staples. If you got, how many you need? Every 6 inches. If you've got 20 feet, the force holding each one, you can do one side and the other, right? Because it's just a 2x4 on top of a 2x12. Over 20 feet, you got 40 of them. 40 times 25, that's 1,000 pounds of downward holding force on one side. Two sides, that would be 2,000 pounds of holding force with staples on every 6 inches, right there. I think that's the easiest way. Now we've kind of discovered staples. I've never used staples before, but they're very useful, as you see. So I think staples would be the perfect way to attach those. Otherwise, you can do screw in from the side, but you're gonna be missing because if you got vertical, it's narrow, so you're hitting it and you hardly hit the other one. You're gonna be coming out all the time. So staples could be a good tool. Use what length? 2 inch if you can. 1.5 inch minimum. Well, no, I'm sorry. You only have 1.5 inch, so you don't want to use 2 inch. So 1.5 inch gets you the. How much penetration do we say we want? We want 1.5 for any fastener as a general rule. Another item is about calculations. How far away from the edge do you want to put fasteners onto anything? The general rule of thumb is either twice the material or twice the fastener. So if you were to do this properly, the staple would be 1 inch from the edge. We have to have 2 inch staples. Twice the thickness of. Oh, I'm sorry. I was thinking about OSB. The most strength you could get out of a connection of two 2x4s, 2x materials. The fasteners ideally want to be 3 inches away from each other. Twice the length, the thickness of the material. If you're bonding, we do a lot of the bonding of OSBs together with another scab. Calculation question based on that basic rule. How far away from how big must the scab be in order to get a solid connection to that of the two pieces? Based on this rule of the fastener should be twice 2x, where x is the thickness of the material. What's the minimum scab that you can put on a crack between two pieces of OSB?
How thick is the OSB?
1/2.
And the fasteners?
Well, whatever fasteners we had. I mean, let's assume we had staples of any width or screws which you can space at any distance. Well, yeah. So you want to nail in 1 inch from the edge, right? So the absolute minimum is 2 inches for that scab. Well, you're gonna hit the edge. You're gonna miss the edge. So make it twice as big. So the absolute minimum for a scab between two pieces of OSB is 4 inches. That's the answer. So if you're doing that for just providing the strength of the material, if there's forces on it, that's different. So for example, when we're joining the trusses, which we did for the 32-foot span, you don't put a 2 inch scab between the two. You don't overlap them 2 inches. No, that's got a huge force of up to 3,200 pounds. Well, 1,600 pounds on each shear thing there. So no, that does not work. I'm saying just when you're let's say you make a break somewhere and there's no other forces, then you follow that rule. Otherwise, you have to. That's the next story. And I'll discuss calculations, just basics of all this stuff. You guys always get the questions like, okay, how big should this be? How big a scab? This and that. How far to the edge? That's all stuff that you analyze in 5 seconds when you're aware of all the calculation. I'm not talking about rocket science here. I'm talking about basics. But there's a number of these basics you have to keep in mind. We'll go over that tonight. I think it's very useful because it will eliminate probably 50% of the questions that exist here, and that's part of the integrated build skill set. Is, as I mentioned, one of the first lectures. You got to calculate, you got to engineer, you got to design, you got to build. If you have all those skills, you get really good, and that's where you're making 95K as a construction manager. That's where you're making $5 million a year as an operator of an operation with 24 people. That's the reality when you have that kind of knowledge. But that's for the 5-year program. That's the outcome. Like if you actually succeed in the 5-year program, you could go on your own, make $5 million running a crew of 24, because you build 24 houses. So it would be like, you could say 2 to 5 million revenue from that when you're building 25 houses a year. 25, you can say if it's like 100K revenue net per house. I mean, those numbers add up when we're comparing ourselves to the industry standard. Now, what does that have to do with solving housing? Well, that means that we have that 100K buffer over the we have an 80K buffer over the competition, let's say. So our build cost was 100K. Industry standard build cost for a similar 1,400 square foot structure is 180K. We've got an 80K buffer. What do we do with it? We can contribute that to the open sector. We can expand the education operations. We can do low income housing. It gives us options because now we have economic leeway to make things happen that are never possible before. It's related to calculations in that we have to get that kind of savvy to understand the details, because that helps us build faster, better, stronger, cheaper, and all that. So, for example, I mean, going back to the trusses, I'll brag on myself again regarding the fact that we eliminated half of the needed trusses. If you went to an engineer, he'll make you put twice as many trusses because they did not use the design that we used. It matters. That's thousands of dollars off the cost of that structure. 5. So we got up to this thing. We're discussing how do you fasten it. Use staples. Roof deck, no mystery there. Just make sure that, I mean, how do you align these things? You got to make sure if you have that roof box in, you can only start at a corner like such as this or whichever, this or that corner. You will end up cutting off the last one, but the first one can go in, bam. Now, if it doesn't end up on a truss, or rather the taper, what's underneath it, not the trusses. Now you've got not 4 inches. Now you have 1.5 inches. So that may veer off. What happens when it does? Move it. These trusses are completely flexible right now. They're completely flexible. You'll move them 1 foot to one way or the other if you want to. When they're supported just on the edges, the middle will bend with some force, like 1 foot, and it will still. So I'm exaggerating, but an inch you can absolutely move that an inch or two easily in the middle. At the end, you're going to get tighter and tighter. But something like a quarter, if you're off a 1/4 inch, move it. It'll probably move a 1/4 inch. If not, I mean, how do you do it with leverage though? So you have nothing to hold on to. So what you do is, let me show it on a diagram, because this is going to be the killer in terms of how fast and good we're going to be able to get the roof on. Let's go to a little doc, the written doc that we do, just to show this very clearly, so that it's completely under your will where that OSB and where the and how you can move that OSB to fit the tapers at the end of the day. Okay, let's go to the Builder Crash Course. We got the work doc is the thing I keep going into. No, not this. Sorry. We're in under Builder Crash Course. We've got the September 25. I'm doing the history. That's the first one. But if you go to plain Builder Crash Course, that's what you get. But then I've got the September 2025, and it's under the cheat sheets here, because what we're doing now effectively are cheat sheets. We don't have full instructions. We don't have, exploded part diagrams and all these assets animations, exploded part animations, and a lot of that stuff is missing, and we generate as we go along. So let's show that real quick, how we put so duplicate the slide. So let's say move like OSB roof sheathing technique. Okay, so we have a joist. And this is once again that if somebody had a computer, they could, while I was talking, somebody would have drawn this already. So you say you have this taper, right? So that would be the taper to which you're attaching. So that's a taper, looking from above, right? So say the OSB. So that's your OSB, big sheet. Call it the OSB. Okay. Say you ended up just like that, and the next OSB is, you barely caught it. Like, that's not good enough. You can, barely caught it. You want to move it to the middle. What do you do? Nothing's attached here. Or say actually, no, say actually this one was attached. No, let's go to the case, let's go walk through various cases, case scenarios of how you move things next to each other. So what you can definitely do at that point is put in a little block, screw it down with a heavy, those black screws. So put in a 2x4, let's say, or more 2x6, because you can put in like 4 screws easily into 2x6. Bam, right there. Put it right there. Okay, I put a block up there. It's in 3D. Can you do anything with this? Well, if you had to move in, like say you do a block that's hanging, in fact, a block that would be like more like this. Oh, here you go. You screwed in a 2x4. If this was the case, if that is the case, easy. Throw in a pry bar there, pry it out. You're gonna get it to the edge. So that's the technique. Get it? And then, okay, but say you had this. Well, that block would push it only further. So what can you do there? Well, you can put a clamp on that, or you can put a block like this, and another one. So screw this one in like this, and then screw this one in like that, and now you have a prying surface. You can throw your pry bar in there, and you can pry it over there. So you got to think like this. Don't say, "Oh, it's out of the way. I don't know how to move it." Because you can do a hammer. Perhaps the hammer is enough. So try that first. If the hammer moves it enough, great.
I remember how we did the other one, yeah, and yeah, we got that done. So, yeah, if we get our the spacing right on the trusses and then the tapered sections on that, get everything on the middle, yeah, shouldn't have to move it too much. I wouldn't think. Yeah, we can pry it over, hammer it over, use a clamp. Oh.
Okay.
Yeah.
So say you do that, bam, you tried all those options, didn't work. What's the last resort? What's it didn't fit? Like whatever we tried to do, it ended up, we removed the 2x6s. We couldn't do it. This is what we could get. Bam. What's the last resort? Cut it. You can't do anything but cut it. I mean, there's no option there. So, and sometimes you don't want to also take measurements. If you moved it out, and you had to move it out where it's definitely not on 24-inch centers anymore, because it could be, one case is where it's off 24 centers and it's not working out. If you're moving it and it's definitely gonna mess up everything else, then maybe consider whether you need to do that and just maybe quit it and just cut it, because then you messed up everything for downstream. So you have to think not only the present situation and the downstream situation, but ideally, this thing goes forward well. And this is where the quality control, like in terms of build quality of what we build on the ground, matters, where if we got everything straight and nice, the faster it goes. And that's the difference between a professional who's cranking out, top 1% pay versus a novice who is going to very easily takes 4 times as much time or up to 8 times more time than a pro. I mean, those are real figures. I mean, we've seen that kind of stuff here, where you can only do so much stuff because you're working against compounded errors, poor measurements or whatever from before, or the lack of awareness of what you're doing, or the steps ahead. So you might have fixed it right now, but then ahead, you just buried yourself into a hole because this created a problem downstream. You have to have those 3 levels that you're keeping in mind at the same time. Okay, so so that's the sheathing layer, and at that point we're pretty much ready for the material on top to make that waterproof, which is, it would save a day like today where had to cover it. Okay, back to the CAD. 7, roof insulation. That goes on. Oh yeah, actually, forgot about the roof insulation there. And then, we forgot about the roof deck, roof insulation there. And from this point, we call it, that's the definition of done for this section, but I would say before we even do the roof insulation, do the roof deck. That gets you easy ability to protect this from rain. We don't want to be raining on this more. As soon as you've got the deck up there, you're ready to start attaching the next truss, because you're going to bond the next truss to this. That assumes you have we already do have those walls. As soon as you're at this stage of deck, start working on the next section so we can divide up then. So
Black bolts, or how did we join it?
yes, for that stuff, do the black bolts, the 6 inchers or 5 inchers. You need how much? You got 2.5 plus half of the OSB, so you got 2 inches on each side, so minimum 4-inch screws. Do not use the 3 inches. I mean, that's going to have minimal holding. Just do 5 or 6 inch. 4, 5, 6. I don't think we have any. We got a lot of the 5-inch ones, so we can use those. Do that. And there we go. Now the back, you see it already. The rain goes to the back. We're good. And then that top sheathing was already there. Well, no, it wasn't already there. The top sheathing goes on when we have done this, right? So we have gotten all this stuff up. As soon as the box is up, you can divide into the roof deck and the side sheathing. Box forks into roof deck and sheathing on the upper side.
Okay.
So we can do those things. All right, so that's what we got. Any questions, or what else do we want to go over today? I mean, let's reinforce. Let's put some spacers underneath for the sagging issue. That's a thing. I think it looks like
So
it
do we need to
cleared
check
up.
the middle one for level? Or is
Yeah, we
it-
do. So
Okay.
check the middle one. It should be pretty good right now. Let's check that we actually have a flat surface there, so that I think we have to unscrew like one wall section where I think that vertical. No, I fixed that one. There's one in the back that we want to check for both the alignment, because that's after the correction. So the last module on one side and the other. Let's check that,
Okay.
and there we go.
And then level the third floor module, make sure it's flat.
Put some
before we're-
spacers
Yeah.
before going on there, and that's the structural part. We can probably get the second section on. Well, let's see how far we get. We don't have bodies, so I mean, let's see what we can do here for the section just to cover one fully. At which point you're ready to do the insulation from the bottom. It's almost getting ready for the thermal aspects and total finishing. You know, what we could do is, I don't know if you guys want to go from this point on. We definitely want to put the decking on to the other sections for rain protection. We can start on a photovoltaic mounting like as soon as we want to as well. So if we do this maybe tomorrow, like we could I mean, you guys probably do you guys want to see the mounting of the PV and all that stuff?
Yeah, sure.
Yeah, and it's exciting because now it looks like, wow, this is cool. This is modern age with wood, which is Stone Age. So that's cool. And then we get the electricity in there. Any questions?
How do you level the middle joist? The middle section, like the
floor.
we can raise them the sides. but
Well, the sides,
middle-
the 4 corners, the 6 points of support are good. We tested that with a level laser, and that was quite tight. So we have that, but we're talking about in the middle of the 12-foot
the-
section.
under the boards. Under
Yeah,
the-
you can't access it. That's
Yeah.
I'm sorry for we missed that. Now the weight is not distributed in the center, so that will sag when there's like 20 people on it.
That's
but
gonna affect the interior walls, right?
well, it will. It will. Now, so yeah, I mean, ideally we would get that. Now the interior walls, they're not load. They are load bearing in some way, but all the weight is on the outer edges, so we're pretty good. After you actually screw in the trusses, which are each of those can handle 50 times 20. Each truss handles so it's 50 pounds. The design is 50 pounds per square foot. Each joist is responsible for 2 square feet times 20 square feet, so that's 400 times 50. So each joist is designed for 2,000 pounds. What that means also is that once we actually screw in to the joists from the wall modules, you're actually helping the floor not sag. So for the interior modules, if you're going to screw into the joists, you're allowing the joists to support the weight of the walls as well, in addition to the floor. So that's how it works. So you got this box structure, so the sag on the third section should be addressed by that itself if we screw in the trusses into the ceiling as well.
We
So
have to install the interior walls before we put the trusses.
before the trusses go on, you could do the interior walls. Otherwise, you're trying to stick
that
in that
side.
top plate. You can do the interior walls without the top plate or with one top plate, and then you have to squeeze in the second top plate where you'd be fighting it and banging it in, trying to bang it in there. But yeah, you want to do that. Do the interior modules before we do that. Yeah.
Also, how are you waterproofing the sections between the roof?
Yeah, so we talked about that a little bit. So you span. I would do the same material, which is the fiber reinforced polyethylene, the 30 mil stuff. You span it. So if we got the walls, so you got the roof. This is what's exposed at the end of the day, right? You got the insulation, and everything is up there. You need to span. So that crack there. That's a rain crack, right? So you need to close that up, and you need to run the fiber reinforced polyethylene up these joists, because that's a crack that goes into your house. So you got to run it up and over. But since we're shipping in 3 parts, we're going to run it up to the edge, and if we have enough material, we just go actually all the way to the top, into the crack. Even if we have, I'm not sure we're going to have enough material, because we designed this with extra material for one piece. We actually did not consider the moving in one. When we started this, we were going to keep the house here, so as a demo house, and that changed. So what we'll do is run the membrane up, so you're addressing this leak here, but then you've got everything at the top. That's a leak point. So you got to cover this whole top, overlapping the membrane that goes up to the edge here. So you're capping it. Think of a cap like that with the same FRP, fiber reinforced polyethylene material, and then you got to protect the FRP from UV. So you trim it up. So put treated wood on top of that, like a box that's got those 3 sides, so you're protecting it completely from UV, and your entire structure is a 100-year roof. So you've just done a 100-year roof. This is awesome. I don't know why everybody doesn't do gravel protected roofs. Well, we know the obvious answer. Everyone has a regular house. You can't do that. You can't put gravel on top of a sloped roof.
It's
So
probably not too cold. Like
it is too cold, as in, it's not. Flat roofs are in code actually. So
like
that's already.
gravel.
Well, no, it is.
Gravel to
It's
cover.
exactly what they do. Yeah, it's called a protected membrane. It's a gravel protected membrane, protected membrane technology. I mean, that's all it is. It's just things like gravel or other things, and they have gravel specs for stuff that goes on a roof, so it can't be blown off by the wind, can't be dusty, it can't be too heavy or sharp that you puncture the membrane underneath. And it's pea gravel works great for that. We can get pea gravel at $50 a ton from the quarry, which is by Kansas City. We'll take our dump trailer once that comes.
So the gravel is basically to protect it from elements.
Elements,
like UV light and all that.
primarily
Also holding it
UV,
down.
Okay.
and it also holds it down.
Because UV
Yeah.
is probably the most destructive thing.
Yes,
all
it
the
is.
time? Okay.
It is. UV will destroy just about anything outside of like ceramics and steels. I mean, any biomass, any organic molecules, UV is in a wavelength range of breaking up those molecules.
I've seen that on my roof, even with the chimneys and some of the plastic I put over those over time. Yeah, the sun will break that stuff down. It's a funny thing. Yeah.
Oh yeah, oh yeah. I mean, UV.
I've got metal buckets in there now. Yeah.
Mm-hmm.
So we're looking at 3 sheets of the polyethylene for the roof. And
Yes.
then they're going to overlap on the seams, so it'll be waterproof but can still come apart for shipping. Yeah.
Mm-hmm.
Okay.
Mhm.
That's easy enough.
So each sheet goes there and up to the edge of the tapers. Yeah.
Okay.
And we actually have to be. Yeah, we gotta make sure we do that carefully, that we have enough because we have basically a long sheet and it has probably like 2 or 3 feet extra on each side, so we gotta cut it right into 3 sections. We can't make too many errors there.
Yeah.
So we gotta measure it carefully.
Okay.
Yeah.
All right, and then it's just going to overlap on the seams. Okay.
So you go up the seams, and then probably for the meantime, just put like a piece of trim up there, put a board up there to close that
So
seam if
to
you
the
want to.
seam, not over the seam. Huh?
Well, so there's 2 pieces of the roofing membrane per section. So you got this one that spans the whole thing, and a second one that goes
Oh, okay. Yeah.
caps
So
over to the adjacent
a narrow strip.
Yeah, a narrow
basically.
strip that you're using to
Okay.
cap that. Now, how are you going to connect it at the sides? I think the proper thing there is you can't put like, you use roof mastic, so use water protection mastic, this kind of gooey stuff. But if you do covering that with trim, you're talking about screw holes or nail holes. You have to put water stop caulking or this roof mastic substance
Okay.
above that, so if wherever there's a puncture, you lay that bead of that caulk
Okay.
above, so that water is not getting into that. So this is like, it's pretty tight. There's that's like another hour lesson on how you actually
Yeah,
make
we'll
that
get to
seal.
that later. We're looking
But-
at 5 pieces. So.
Yeah, 5 pieces, and there's detail which, yeah, I mean these are the kind of critical details that an inexperienced person will have. Like when I was looking at vinyl siding and the way people do it, I can tell you all the houses, most or vast majority of houses leak at penetrations. The way they do it, even the industry standards, they're not seeing them up. Whenever you have, that's with vinyl siding. I mean, yeah, you have all kinds of trim pieces, but the way they do it, I mean, it's actually pretty, it's pretty like primitive, if you may say so. It's once again because it gets into that detail where they don't, like the inspector never really catches that. Like you can't really inspect it, and the codes, they tell you the general things, but people like you can't inspect for it and all that. So a lot of times, I mean, leaks are a common thing in houses, right? And very few people know how to do this properly. So I think we know how to do it quite well actually by this time. So with flat roofs, we're not making very deliberately. There's no penetrations at all on the top. I mean, don't
That makes
even.
sense.
Well, we've got the cracks right now to address, but forget about that. Just redesign it so that you're not making any penetrations for the concept of lifetime design. It's always, 20 years down the road, whatever, 50. If you have penetrations, you're gonna get leaks. So it's just get it out from the start and send everything out the sides, and sides are much easier to seal up than the top.
We ready
Yep.
to get going then?
Okay, so let's get going. We'll quit this discussion. We're gonna rejoin back for 6 p.m. Yep.